Is the motorcycle problem. All right, so here we got motorcycle guys just going over a hill, right? Is that correct?
Yes.
All right, so we're going over the top of a hill. I'm sure we have some indicated radius of curvature for the hill, which is 25 meters, 125 meters. All right. We'll call it, instead of 125, 126. All right, so motorcycle guys going over, and at first we're given an initial velocity, right? Or we're given the speed at the top. Is that correct?
Yeah.
All right. How many?
25 meters per second.
All right, V is equal to 25 meters per second. All right, how many of you guys draw pictures like this when you solve these problems? Good, we're getting there. All right, do they have to be beautiful Leonardo da Vinci type pictures?
Yeah.
No, just for Remy. His just turn out that way. All right, so the first question is, what is the centripetal force at the top of the hill? All right, well, this one should be really easy. All right, centripetal force at the top of the hill, it doesn't ask anything about where it comes from. It's just asking about how much force do we need to stay in a circle of radius 126 meters if we're moving with a velocity of 25 meters per second. It's that simple. Okay, so centripetal force is just equal to mass times centripetal acceleration, which is m times v squared over r. All right, so centripetal force is equal to, did it give us the, I'm assuming it did give us the mass of the motorcycle.
Yep.
And rider.
Yep.
Okay, what is it?
342 kilograms.
342 kilograms? 342 kilograms times centripetal, centripetal acceleration, velocity of 25 meters per second. We're going to square that and divide by the radius of the hill, which is 126 meters. All right, so taking this, just all we got to do is plug numbers in. And after we do that, what do we get? Calculator people, where's my calculator brigade?
169.
169 newtons. All right, that's a little over precise. I think it's fair to call it 1700 newtons. 2 sig figs there. Did it say 25.0 meters per second or 25?
25.
Just said 25? All right. Oh, yeah? All right, well, actually, that still turns out the same, doesn't it? As far as sig figs, kind of weird. That makes, we should give it as 1.70 times 10 to the third, right?
Yep. Chemistry.
Times 10 to the third newtons. What's another way we could express 10 to the third newtons? 1.70 kilonewtons. Thank you. Centripetal force. All right, that's part A. Resuming with part B. B for blue. All right, so the question is, what is the magnitude of the normal force acting on the motorcycle? Is this normal force acting on the rider or the motorcycle? It's on the bike, right? Because it's not separated. We don't know what the... Okay. All right, so this situation, same picture. Okay, same picture here, but now instead of a physical picture, we'll do a free body diagram. All right, so we have what acting downward? Easy. Okay, mg. What do we have acting upward? Normal force. Okay, any other forces acting on the motorcycle as it goes over the top of the hill? We're ignoring air resistance, so we'll just say no. Say it. All right. All right, so here, that's what we got going on. So, how much force do we need? Net force equals mv squared over r. Where does the force come from? We got a normal force acting upward. In this situation, I know that I say lots of times we should use the center of the circle as the positive direction. Not really necessary in this case because mv squared over r, yeah, let's do that. Let's do that. Because mv squared over r, I'm giving it as a magnitude, because what direction is mv squared over r actually acting? Upward or downward? It's actually acting downward, okay? So if we make downward positive, that's towards the center of the circle, okay? Does that make sense? All right, so here we have, in the positive direction, we have mg, and in the negative direction, we have n. It's sort of counterintuitive here, but it's going to end up being the same way anyway, okay? because of canceling negative signs. So mg minus n is equal to mv squared over r. Can we cancel the m's? Not yet. Well, not ever. Okay? Because what we're solving for is normal force, right? And we don't know how normal force is embedded somewhere in that, in the mass is somewhere embedded in that normal force, but we don't really know how right now. Okay? We don't have enough information. But let's solve for what that would be. All right, so we're going to get n is equal to mg minus mv squared over r. Put this over here. Yes, mg minus mv squared over r. Is that correct? Does that make sense? Is that possible? Okay, because if we're going 0 miles per hour, what's the normal force? mg, right? Does that make sense? Okay, so if we're going over the top, is the normal force going to be less or more than mg, do you imagine? Think about it when you go over the top of the hill. Do you feel lighter or do you feel heavier? You feel lighter, right? So in other words, the normal force is going to be decreased by the fact that we're going over the top of a curve. Okay? Over.
Sorry, mg minus n. So
mg's acting towards the center of the circle. We're taking the center of the circle to be positive. Look, Omer, what I was saying was, we could say if we take upward to be positive, it would be n minus mg, but the mv squared over r here would have to be negative in that circumstance, right? In that frame of reference? Okay, so, you see what I did right here when we talked about this? Think about that all the time. When you set up an equation like that, think about, if I experience this, is this consistent with what I would expect? Right? Sure, as you go over a curve, the faster you go, the lighter you feel as you go over the top. Right? So the bigger I make this term over here, the mv squared over r, the smaller this n term will become. All right? And it's consistent with our experiences. All right, so n is equal to m times the quantity g minus v squared over r. This looks a lot like what, by the way? Yes, it does. Doesn't it look just like the elevator equation? Because this is g plus a, right? But plus is downward, so it's a little bit weird, but it has a similar structure. I'm glad you guys recognize it. That's pretty cool. All right, so m is equal to, what was it, 342 kilograms. And g for this one, let's just estimate 9.8 meters per second squared. And minus, v was, we just did this up here, right? Oh, wait, we didn't do it because we had the m in there for the total force. 25 meters per second quantity squared over 126 meters. All right, did somebody crunch all that out already? The normal force? 1.66 kilonewtons. All right, 1.66 times 10 to the third, or 1.66 kilonewtons. All right. All right, so part C for this motorcycle problem, the part that I made up myself was, what is the maximum speed that the rider can go over this hill and not lose contact, right? So again, we have a radius of 126 meters. We know that we're going to go up like this. We're going to have some velocity at the top at our center of mass. So I call this VC for V critical, right? What's this critical velocity? All right. So in this circumstance, we have a new free body diagram because what has happened? We still have mg acting downward, but what has happened to the normal force? It's decreased all the way. Look, let's go back and look. Remember, the bigger we make v squared over r, the smaller the normal force gets right here, right? So if we make the velocity big enough, the normal force will go away if we set mv squared over r equal to mg. So we're solving for that situation where the normal force is equal to 0. We can already see that we're just going to be setting mg equal to mv squared over r. But let's take a look. All right, so we got mg acting downward, and that's it. That's the whole thing, the net force. So net force is equal to, here's our two-question strategy. How much force do we need? Net force is equal to mv squared over r, and net force is equal to, from our free body diagram right here, just like we said, what? mg. All right, so net force is equal to mg. And like we sort of figured out from the previous equation, we were saying where is the net force going to be, the normal force going to be equal to 0. And since this minus this was equal to the normal force, we set that equal to 0, then they are equal to each other. So mv squared over r is equal to mg. All right, I won't use the old joke now, pretty much worn out that. And so v is equal to the square root of gr. All right, so v is equal to the square root of 9.8 meters per second squared times the radius of our curve, or radius of curvature, 126 meters. Meters squared per second squared, square root is going to give us velocity in meters per second. All right, so velocity is equal to, what does that crunch out to? 30 what? 35.1 meters per second. All right, probably a little bit too much precision, but that's not one we'll get squirrely about. 35.1 meters per second.